So welcome again to another video for numerical method. And for the past videos, we have been talking about finding roots of equation. Then we introduced bracketing method. So in this video, we are still in finding roots of equation, but we are proceeding in the open method. So in open method, there are actually many methods, no, that you can choose. So we have simple fixed point iteration, we have Newton-Raphson method, we have secant method, modified secant method, the branch method, and the multiple roots. So in this video, we will be limiting to explain uh, simple fixed point iteration down to modified secant method. So for what I understand, simple fixed point iteration and Newton-Raphson, I think those are the basic methods for open method, no? Because second method is the modified Newton-Raphson, and then it is being improved, then it becomes modified second method. So again, so modified second method is the modified of the Newton-Raphson. So there is two revisions for the Newton-Raphson. Anyway, let's proceed with simple fixed point iteration. So for simple fixed point iteration, the process here in finding the roots of equation. So let's say you have um, a governing equation. So our governing equation, let us say f of x, no? And in finding, let's say, the problem requires you to find the roots of the function. So you will equate your function, your governing equation to 0. And in algebra or in analytical method, uh, you will play with the equation until you will find the value of your x to whatever the function or equation is. It might be an algebraic, a rational, a trigonometric, so on and so forth. So what happens now in simple fixed point iteration is uh, you will create a new formula. So that formula will be your iteration equation that you will use every time for every iteration. So let's just say you will split your original function. Your original function is the f of x to g of x. So the new function plus the extracted variable x. So yeah, so magkuha ka og variable x, so one single x out from your original function, then the remaining is a new function which we could call as g of x. So that one. So let's just say that the combination of the single variable x and the g of x will be equivalent to your original equation. And this scenario, so you will let the single variable x on the left side and the other remaining equation or variables onto the right hand side in such a way that your new iteration equation in using simple fixed iteration or in finding roots will be this one kaning naa sa picture nakipakita. So your new root will be the equivalent value when you substituted your present root to the g of x or to the new function that you modified. Okay, so I will show you how you will execute this one, but before I will show you, let's stream down all of the methods in open method, no, katulang upat. Then we will try to execute that for method onto the same problem that we solve from the bracketing method. then we compare after. So proceed lang sa top. So for Newton-Raphson, so the idea of the Newton-Raphson is based on the uh, geometrical interpretation, the alternative method based on the Taylor series. Uh, if you try to recall, no, ang katong pag-solve sa uh, the derivation of the function is was based on the solutions on the tangent problem or the velocity problem. So katong slope of the tangent line, which is the change in y over the change of x. So then atong take ang limit ato, then we then find the value of the slope. So same scenario here, we copied those solution. So your derived function, no, will be equivalent to your f of x sub I minus 0 all over the difference of the present root and the new root. So there are 4 elements here in the derivation of the function. And then you arrange this equation, then you will have a formula in finding your new root in such a way it will be equivalent to the present root minus the the value when you substituted the present root to the function all over the value that you substituted the present root to the derived function. So yeah, this method may be impractical, no, in some ways, because uh, you will need to derive the equation first so that you could have an iteration equation. So in some ways, the purpose of numerical method is to have an easier solution, no? Uh, yeah, to have an easier solution, then why in Newton-Raphson we need to derive the equation first? So there's no sense, no? So imbes na pwede raw na to algebraic ato ang solution in analytical method, in Newton-Raphson nag-derive na noon ta. So yeah, but the Newton-Raphson is kind of the foundation of the second method. So in the second method, dili na ta kinahanglan mag-derive. So ato lang i-let it be na in ani ang way sa Newton-Raphson. So the graphical depiction of the Newton-Raphson method is this. So the blue curve represent the f of x. The f of x. So open method, Newton-Raphson method is an open method which requires you only one initial guess. Let's just say it represents x sub I. So for your initial guess, that will be x sub 0. And when you plot your x sub 0, let's say this one, and you'll try to find that root based on the formula from the slope of a tangent line. So however, you will find this value out from what you learn in differential calculus. So you need to know how to derive first the equation. So para makuha ni nato. So you will have your slope of the tangent line, and then you have this equivalent point here, and this line here, for which mura siya ato ang reverse engineering ang katong equation sa tangent line so that we could get the new root, the x sub the x sub 1, or your new root, x sub I plus 1. So notice that when finding your x sub I plus 1, it becomes closer and closer to the root, no? So when you execute another iteration, let's say this one, then you create again the tangent line, so it becomes closer to the real root. So the real root is this one. So in ana ang pag-solve sa new root and finding the roots of equation in Newton-Raphson. So in a graphical explanation. Okay, so let us proceed. So in secant method, same idea, no, are we but yeah, we are copying the formula from the Newton-Raphson, but notice that we have substituted the value of your derivative function. So ang original formula sa Newton-Raphson method is your new root will be equal to the present root minus your f of x sub I all over your f derivative of f x sub I, no? Then in second method, kipangitaan niya value ang imuhang derived function para dili na ka mismo mag-derive. And higamitan niya og kani siya backward finite divided difference, for which I will just not explain it how it gets here. So ang kani siya na there are many formulas, no, for the derivative of function. You could have forward, you could have centered finite divided difference, but in second method he uses the backward finite divided difference, for which the equivalent equation for that it's is the the value of the value of the substituted what we call this root that is one step backwards when you substitute it, no, mo na ang equivalent value sa katong function, then minus to the substituted the value of the function that substituted the present root all over the difference between the root of the let's just say x sub I minus 1 minus x sub I. So ang katong previous roots minus the present root. So yeah, then you substituted that equivalent value to the original Newton-Raphson, the original form of the Newton-Raphson method. Then emotion kimutang dere, then you are modifying the formula, then you get a new formula in finding the roots. So mo ni siya, no, the new root would be the present root minus the f of x sub I times the difference of x sub I minus 1 minus x sub I all over f of x sub I minus 1 minus f of x sub I. So, okay, wala na tay derivative function, so okay na. But however, notice that in this equation, you have two types of x's here, the x sub I and the x of I minus 1. So, you need two initial guesses again. So, hala sir, two initial guesses, and why dili siya mabelong sa bracketing method. So di siya mabelong sa bracketing method is because the way that the way that that you execute the equation second method is you are not closing or you are not bracketing the curve, but instead you just need those two initial guesses to execute properly the solution in finding the roots of equation. So you get the idea no ngano naabot pa gini siya sa modified second method. It's because kani siya na part is you need at least two initial guesses, which is kind of a hassle. So siya. So in ani ang graphical deflection sa second method, since we have two initial guesses, then ang katong two initial guesses ato niya kay imo siyang ki-combine no kay you have two equations. The one is ang katong usa is like a forward finite difference, then ang katong usa is a backward finite difference. Imo siyang ki-substitute to each, so nag-create kag one equation for that, so it makes a line. So instead na ang katurang usa, so let's say ang kani kay supposedly in ana siya, no, then mo ana siya, so those 2 points will create one line and create an intersection of the x-axis. So ma-determine niya ang katong point na intersect sa x-axis, and that will be your new root. And notice that ang katong second method ay ang katong Newton-Raphson mas layo siya no compared sa second method na mas duol sa real root nato. Yeah. Okay. So modified second method. So what happened is because of the issues of the Newton-Raphson and the second method. So sa Newton-Raphson, there is what you need to derive the equation. In second method, you need at least two initial guesses. So that issue is being resolved in modified second method, for which instead that you will need to have a backward root or the backward value of x, no, you have at least kanang create na lang mismo the katong uh, the second value of x, so by multiplying a certain amount, a certain number, no, which is what we call as the perturbation factor. So perturbation factor, or in the equation it is the small Greek letter sigma. So usually the value is 0.01 or 0.001. The lesser as it can get, the better the equation. So what happens now is that the difference between the root and your initial guess and to the other guess that generated automatically will be smaller, and based on based on experiences and based on solutions in differential calculus, when you have smaller difference, you have more accurate data. So katong tangent and velocity problem, no, when you have a difference of 0.001, you are fastly approaching to a certain value, and that's how we are trying to copy that idea here. So yeah, so we have this value, no, for your derived function. Then we put this to to the Newton-Raphson method formula, then modified again the formula in such a way that you will create a new formula for the new root. So, muna siya no, new formula. In which it kind of resolve the problem no, because the formula for the method modified second method is that you only require one initial guess only. And you will not need to derive the function or the governing function